Hi. In continuation to our discussion on electrostatics, we try to discuss today Gauss law and its applications. So, the topics of discussion are trying to understand the concept of electric flux density, what is Gauss law, and what are the applications in terms of electric field calculation due to a point charge, due to infinite sheet of uniform charge, then field of uniformly charged sphere, which also can be done using your regular Coulomb's law, but how we do it easily with a Gaussian surface defined and using Gauss law by itself is what we try to understand through this lecture. So the electric flux density, as such, if we are trying to understand this concept, can be understood by Faraday's experiment, where we consider a set of concentric metallic spheres, where the outer one consisting of two hemispheres which could be firmly clamped together. Let us say, with the equipment dismantled, the inner sphere was given a known positive charge. The hemispheres were then clamped together, and around the charge sphere with about 2 centimeters of dielectric material between them. The outer sphere was discharged by connecting it momentarily to ground, and the outer sphere was separated carefully. Then what happens is we see that the negative induced charge on each hemisphere was measured, and it would be showing us that the total charge and the outer charge was on the outer surface was equal to in magnitude to the original charge on the inner sphere, and this was true regardless of the dielectric material that is connecting the two spheres. So there was some sort of displacement from the inner sphere to the outer sphere, which was independent of the medium. This, as the displacement flux density or the electric flux, is represented by psi and is called the electric flux density, which is equal to q. And the electric flux is measured in coulombs and is represented by the letter d, and because of the name that was initially given, that's the displacement flux density. The direction of t at a point is the direction of the flux lines at any point, and the magnitude is given by the number of flux lines crossing a surface, normal to the line divided by the surface area. So we can see this here in the figure. If you see, the inner radius is r equal to a, outer radius is r equal to b. The inner sphere is charged positively with the charge of plus q, and outer charge is minus q. So in between, the pink color indicates the insulating or dielectric material. The electric flux density in the radial direction has a value of d equal to q by 4 pi a square ar, or t equal to 4 by b square ar for r equal to b. So once we say that at a radial distance a between a and b, d will be generalized and will be equal to q by 4 pi r square ar. If we compare this result with our existing definition for electric field, where we have understood that E equal to q by 4 pi epsilon naught r square ar, so we can correlate the electric flux density and the electric field intensity by the relationship d equal to epsilon E. So this relationship T equal to epsilon E is a very fundamental equation and very important throughout our studies on electrostatics. Now, the figure shows clearly what is the flux passing through an open surface. And for a generalized volume charge distribution, E and D are given by E equal to volume integral of rho v dv 4 pi epsilon naught r square ar, or D equal to volume integral of rho v dv 4 pi r square ar, where the difference between these two, the electric flux density and the electric field intensity, is the permittivity term that we see in the denominator. And from the above, it can be seen that the electric flux passing through any imaginary spherical surface lying between two conducting spheres is equal to the charge enclosed within that imaginary surface. This charge, that can be a charge that is distributed on the surface of the inner sphere, or it may be concentrated as a point charge in the center of the imaginary sphere. So how we consider the charge is varied, and also as 1 coulomb of charge produces 1 coulomb of flux, the inner conductor might as well be a cube or a queer of metal or a brass door key, and still the total induced charge on the outer sphere would still be the same. The flux distribution will no longer be the same as the previous symmetrical distribution, but it will be unknown distribution. If the outer sphere is replaced by a closed surface of any odd shape, still the result will be the same. So the generalization of the concept that we are trying to understand is known as the Gauss law, which says that the electric flux passing through any closed surface is equal to the total charge enclosed by that surface, and Gauss law constitutes one of the fundamental laws of electromagnetic theory. If the flux emanating from a closed surface is then given by xi equal to q enclosed, it in its general form is given as surface integral of d dot ds equal to volume integral of rho v dv, which is very important law which helps us in evaluating electric field without using complex formulas and complex equations that have to be derived for different shapes when we are having different charge distributions. So by applying divergence theorem to the first term in the equation that we have just seen, surface integral of d dot ds equal to volume integral del dot d dE, or this is equal to volume integral of rho v dV, which gives us the one of the four Maxwell's equation, which is del dot d equal to rho v, or surface integral of d dot ds equal to volume integral of rho v dv, which are the differential form and integral form of Maxwell's equation, which forms one of the first derived Maxwell's equation for electrostatics. The next important aspect that we have to understand are what are the applications of Gauss law and how we use it in order to evaluate a particular electric field intensity based on a particular charge distribution. The procedure for applying Gauss law to calculate the electric field involves first knowing whether symmetry exists or not, because without symmetry, it is not possible to apply Gauss law. And once symmetry exists, we can evaluate the electric field or the charge distribution. Based on the charge distribution, we can calculate the electric flux density. Once symmetry charge distribution exists, we construct a mathematical closed surface which we call the Gaussian surface, and the surface is chosen such that d is normal or tangential to the Gaussian surface, and when d is normal to the surface, d dot ds equal to dds, because d is constant on the surface, so radially outward, and d is tangential to the surface, d dot ds would be 0. Thus we must choose a surface that has some of the symmetry exhibited by the charge distribution, and we'll try to apply it to some of the applications like the point charge, for instance. Suppose a point charge q is located as shown in the figure, and then to determine d at a point p, it is easy to see that choosing a spherical surface containing p will satisfy symmetry condition. So q is a point charge, and we have taken a Gaussian surface which is a sphere, which is symmetrical around this point charge, and then there's a spherical surface centered at the origin is the Gaussian surface as shown in the figure. And then since d is everywhere normal to the Gaussian surface, we define d equal to dr ar applying Gauss law, and the charge enclosed would be given as q equal to surface integral over the closed path d dot ds equal to dr integral closed path ds, which gives us dr 4 pi r square. And then this can be evaluated based on spherical coordinates as theta equal closed path integral of ds theta equal to 0 to pi, phi equal to 0 to 2 pi, r square sine theta d phi d theta equal to 4 pi r square. The surface area of the Gaussian surface, which yields us d equal to q by 4 pi r square ar, and similarly e equal to q by 4 pi epsilon naught r square ar, which are what we have derived earlier, like the electric field that was derived earlier based on Coulomb's law. Similarly, infinite line charge can also be uh, infinite line charge electric field intensity can also be evaluated. Suppose the infinite line of uniform charge rho L coulomb per meter lies along the z-axis. And then we are trying to determine d at a point P. We choose a cylindrical surface containing P to satisfy symmetric conditions as shown in the figure. So here we have the line charge rho L coulomb per meter along the z-axis, and then we have a Gaussian surface defined which is symmetrical around this uh, line charge, which is around this particular z-axis, and then which is of length L, and then let us say the radius is rho for the cylinder, and then we are trying to evaluate at a point P the electric flux density, then we can define that d is constant on the is constant on and normal to the cylindrical Gaussian surface, and d equal to d rho a rho. If we apply Gauss law to an arbitrary length L of the line, rho L into L will be equal to q, or integral d rho ds equal to d rho integral ds, but this gives us d rho 2 pi rho L, where rho is the radius and L is the length of this particular cylinder. So evaluating the integral of the closed path ds over the closed path, we would end up getting 2 pi rho L. L is the surface area of the Gaussian surface, and double integral of d dot ds evaluated on the top and bottom surfaces of the cylinder is 0, since d has no z component. That means d is tangential to those surfaces, and then as such d would be yielding us the value of rho L by 2 pi rho a rho, or E as such will be rho L by 2 pi epsilon naught rho a rho. And then similarly, the derivations for infinite sheet of charge can also be done easily with Gauss law, which would take numerous steps when we are taking other methods to calculate the electric field. Consider the infinite sheet of uniform charge rho is coulomb per meter square lying on the z equal to 0 plane. To determine d at a point P, what we choose is we choose a rectangular box that is cut symmetrically by the sheet of charge and has two of its faces parallel to the sheet as shown in the figure. As d is normal to the sheet, as such d would be dz az. And then applying Gauss law, we end up getting rho is integral ds equal to q equal to integral over the closed part d dot ds equal to dz integral over the top surface ds plus integral of bottom surface ds. Then we end up getting d dot dx evaluated on the side of the box to be 0 and has no components along ax and ay. If the top and bottom area of the box area each has area a, then above equation rho is a equal to dz a plus a, and thus d equal to rho s by 2 az, or e equal to d by epsilon or rho s by 2 epsilon naught az. So similarly, we can also calculate the uniformly charged sphere electric field intensity, and then considering, let us say, a sphere of radius A with a uniform charge of rho v coulomb per meter cube. To determine D everywhere, we consider the Gaussian surface for cases R less than A and R greater than A. Since the charge has a spherical symmetry, it is obvious that a spherical surface is an appropriate Gaussian surface. So taking this particular uh, diagram, as you can see, the Gaussian surface is a sphere here again, and if we are considering the case where charge density r is less than r, E will be equal to rho 4 by 3 pi r cube by epsilon naught, or E into 4 by r square equal to rho into 4 by 3 pi r cube by epsilon, or E equal to 1 by 4 pi epsilon naught q r by r cube. And for r equal to r, your our E value would be 1 by 4 pi epsilon naught q by r square, and for r less than r, E into 4 pi r square would evaluate to q by epsilon naught, or E equal to 1 by 4 pi epsilon naught q by r square. If we try to understand it graphically based on the radius and the electric field, if we try to plot it, we end up seeing that this would be a straight line up to r equal to r, and for r greater than r, it would be a dropping down. So for r less than a, the total charge enclosed by the spherical surface of radius r, as shown in the figure, is q enclosed equal to rho v dv, rho v dv equal to phi equal to 0 to 2 pi, phi theta equal to 0 to pi, r equal to 0 to r square sine theta dr d theta d phi, which evaluates to rho v 4 by 3 pi r cube, and xi equal to over the closed part d dot ds dr integral ds equal to phi equal to 0 to 2 pi, theta equal to 0 to pi r square sine theta d 3 phi, which gives us xi equal to dr 4 pi r square. So hence xi is equal to cube enclosed gives dr 4 pi r square equal to 4 pi r cube by 3 rho v, or d equal to r by 3 rho v r for 0 less than r less than a. So for r greater than a, the Gaussian surface as shown in the figure here can be evaluated, and then the charge enclosed by surface in the entire charge in this case would be q enclosed equal to rho v dv equal to rho v dv equal to rho v into 4 by 3 pi a cube, while xi equal to d dot ds equal to dr 4 pi r square. Hence dr 4 pi r square equal to 4 by 3 pi a cube rho v. And evaluating this expression, we end up getting d equal to r by 3 rho v ar for 0 less than r less than a, and a cube by 3 r square rho v r for r greater than a. And this is a sketch that we can see for the variation of d versus r. And in other words, we can understand that d must be constant on the Gaussian surface based on this particular derivation. These are some of the references. Thank you very much.